Hello everyone, welcome to another live coding, where today we'll be doing two things. We'll be first looking at how to use a TensorFlow Hub Model to import it into a custom layer. And the second thing we're going to do is to look at metrics. And we'll be looking through some of the metrics in PerceptiLabs and trying to understand what exactly they are. So we'll be looking at the confusion matrix, we'll be looking at precision and recall, and also a bit on the gradients and F1 score and things like that. So yeah, let's get started. Starting with the TensorFlow Hub model, I'm just jumping over to PerceptiLabs here, and I'll be creating a model using the COVID-19 datasets. I already have it local, so I'll just use that. And we'll be using this one both for looking at different metrics, but also for the pre-trained model. So I'll put input, targets, everything as usual. We're doing image classification. That's why we have the image as input and categorical as targets. When we're in a model, all we're gonna do, we're gonna choose a vision transformer. Martin did a post in our forum, forum.perceptlabs.com, not too long ago about how you could use a vision transformer inside of PerceptiLabs as a custom component. And the vision transformer in question is this one. So it's fine-tuned on ImageNet 1K, and you can see a bunch of detail of it here. What we're essentially going to do is copy this link and use it like this. But before we jump into any of that, we'll first just delete the convolution layer. We're not going to need that any longer, since we'll be using the vision transformer instead. And we'll drag in a custom layer, which will connect up, and then press open code. All right, so here we have a completely customizable component or layer. And what I want to do here is first we're going to want to import TensorFlow Hub. And the second thing is to actually use and run the model. So the current custom layer is missing a function called build, which you have in Kira's functions as well. We'll soon adding it, so it's we'll soon be adding it, so it'll automatically generate here, and you'll always see it. But for now, we'll just do like this, def build, it'll take self, it'll take input shape, which is just something we use. And in here, we can then set up any function or anything which we want to use. So here, and the difference between the build function and the call function, real quick, is that the build function only happens once. It happens when you build a component, while the call function happens every time you do any inference of the component, anytime you run through it at all. The problem with having it in the call function instead, which you could do, you could put some function in here. The problem with that is that it's going to call the hub every single time, and that will cause some crashes during training. So instead, we're just doing like this: for TensorFlow Hub as hub, and it comes as a requirement with PerceptiLabs, so you'll already have TensorFlow Hub installed if you have the latest version of PerceptiLabs. And then we will create a VIT, a vision transformer. We'll create it as a self variable because we'll be we'll actually initialize the model here, and then we'll use it up here. It's a hub, Kira's layer. Then we go over back to here. We'll copy the URL where it's placed, and just place it in here as a string. And then we'll go back up and we'll set output equals to self.vit of inputs. And I'll save it. I'll take a little bit time to download or to load it, either because it's you need to download it from TensorFlow Hub, or if you already have downloaded it, it's a fairly large model, so it'll take a little bit of take a little time to initialize. Then we just connect the rest up, and we have a hopefully working model. So that's how we build or how we use a TensorFlow Hub model in PerceptiLabs. You essentially just plug it into a custom component. Later on, we're likely going to add a component where you can write the URL instead and it does it for you. But this is an easy way to do it right now. All right, so let's run this and see how well it goes. So I'll run it for 5 epochs. This particular dataset is fairly easy, so it shouldn't need too much. I can see training. So there we go. And we got 76 training accuracy and 76 validation accuracy, which is decent. We don't need more for now, just to showcase what the different metrics are and how they work. So we can start looking at the metrics here during training. And we'll have, as you might know, we have metrics both during training and then in the evaluation phase. And they accomplish slightly different things. The ones in the training, the goal here is to make sure that you always know if you should stop the training, go back to the model, and change something up and train again. While the ones at the evaluation can be a little bit heavier. They'll let you dig into it a bit more, and it's something you can do to more evaluate your model in depth, rather than something you would do on the fly as you're training. So to that end, 2 of the more important metrics is the loss and the accuracy. The loss, real quick, is the error of your model. So the lower the loss is, the better. Make sure that validation loss and training loss both go down, so that validation, if validation starts going up while training is going down, that means that your model is overfitting, and it's essentially learning so well on the training data set, the part which it updates on, that it starts being unable to classify or properly predict on the validation dataset, which is untouched from training. It's just there to show if something starts overfitting or not. Accuracy, very similar. It's how accurate you model it. Don't need to go into depth. We'll come back to the predictions for each class after we looked at the confusion matrix in the evaluate. And similarly, we'll come back to precision recall and F1 after that as well. But other interesting parts herein is for each component, you can click on them and you can zoom in, which is a way for PerceptiLabs to open up the black box. it makes it easy to inspect all the different components that are inside of your model and make sure that they operate correctly. So in this, you can see what the output, you can see the weights and biases, and that's all good. But the more important part of these ones are the gradients. The gradients is how your model is updating. So every iteration, every time you send a batch through your model, it's going to do a forward propagation where it predicts on the sample you're going to get this output, and that's your model's prediction, what it thinks the input should be. Should be COVID, normal, or viral pneumonia, for example. And then I will do a backward propagation with the error or the loss, and it will, according to that loss, update each of these components. Now it updates it based on the gradients. Every weight inside of the components or between the components get updated according to how the gradients look like. So these tell you how your model is changing. And two obvious really quick things you want to look for here is, are the gradients zero? Meaning, is the model no longer updating at all? Or are the gradients becoming really, really large? Is the model updating way too much each time? Is it so it's just oscillating between answers back and forth? It's forgetting everything each step. That's what it would mean if the gradients are too large. And at some point it will cause an overflow error and your model will just crash. So those are the two natural things to look at on the gradients. Are they zero or do they go towards infinity? Some other key things about the gradients. You're typically fine just looking at the last component's gradient. All updates which happen here gets propagated backwards. If nothing is happening in the last components, it's very rare that something is going to change in your model. And you can of course click through and double check that that's the case, but it's fairly safe to assume that if gradients are acting out here, they'll be acting out in the rest as well. Then what we're actually looking at here, each of these steps on the x-axis is each iteration, and it's essentially a time axis from when you start training to when you stop training. So you can very easily follow how it changes throughout time. So you can see if they start really large and then they start going smaller and smaller, which is a pretty good behavior. That means it starts training. It changes a lot at the start of the training and it changes very little at the end of the training. That's kind of how you want it to happen. We're also only showing minimum, maximum, and average. There are a lot of gradients in your model. So this is a summary of it. This is enough to see if they're exploding or they're going to zero. It won't give you the 3D map, which you might have seen in TensorBoard, or which you can plot somewhere else, where it shows you exactly the weights step by step and how they change. But it's at some point that becomes a little bit overflow of information to look at during training. So yeah, those are the some of the more important things to look at while you're training. Is the loss fine? Are we overfitting? Is the accuracy looking better and better? And are the gradients looking decent? This one's pretty interesting as well. It's a confusion matrix, which we'll go over very soon. But what this one does, one very quick and easy thing to extract from this one is, if everything is one color, like viral pneumonia, for example, then things are okay. Or things are really good, rather. The more mixed the colors are here, the worse it's predicting. So for normal, for example, it's predicting a mix of COVID, normal, and viral pneumonia, instead of just predicting normal where it should be normal. Okay, let's move over to the evaluation, or where we can run a test. Let's select the model we just created. And here we'll get a confusion matrix together with some statistics. We'll be ignoring these statistics for now. I'll quickly cover what top 5 means, but let's focus on the confusion matrix. So this is the other way to visualize a confusion matrix compared to the one we just saw in training. And what the confusion matrix tells you is that for 9 samples, it predicts COVID 9 times. Rather, it predicts COVID where it should be COVID 9 times, predicts normal where it should be normal 11 times, and it predicts viral pneumonia where it should be viral pneumonia 5 times. So that's the baseline of it, where it predicts correctly. Then we can look at the other squares and see where it's not predicting as well as it should. So for example, when it should be normal, it's actually predicting viral pneumonia 4 times. And it's predicting COVID. Sorry, I mixed it up. It's predicting viral pneumonia when it should be normal 4 times, and it's predicting viral pneumonia when it should be COVID 3 times. And you can read it here where the actual ones is where it should be. That's these rows. And down here is what it actually predicts, these columns. And similarly, here it's predicting normal when it should be COVID 1 time. All right. So that's how you read through a confusion matrix. You can essentially see what it's predicting and what it should be predicting, and how many times it does correctly or how many times it does it falsely. From this, we can calculate the precision and recall. Now, precision and recall are 2 fairly popular metrics to use, and what they essentially say is precision is how rarely you predict something other than what it should be. And let me show what exactly I mean by that. So for example, for normal, for all my predictions in normal, I predict normal as 11 times. So correctly predict normal where it should be normal. But I predict normal where it should be COVID 1 time. And this is what precision tells you. It tells you how precisely, when I predict normal, how correct will that prediction be? In this case, it will be 11 over 12, which is, with the calculator, 92%. So if I predict normal, it's a 92% chance of being correct. Awesome, that's pretty good. And that's another way of seeing precision. It's essentially how precise your prediction is. You can think of it. Now recall. So for precision, you might have seen we looked at the columns. So we just summed up the columns and we divided the center part, or the correct predictions. For COVID, we have 100% precision, which is fantastic. And for viral pneumonia, we have pretty bad prediction. We have what's that? It's under 50%. It's 5 over 12. It's 41% is our precision for viral pneumonia, which means that if we're predicting viral pneumonia, it might as well be normal or COVID. It's actually a higher chance of being something else than viral pneumonia. Recall is the other part of this metric. Recall is how often we identify, or how many percentage of the cases we correctly identify. So going back to normal, We predict normal when it should be normal 4 times. We already covered that. However, we predict viral pneumonia when it should be normal 4 times. And our recall will then be the 11 divided by this entire row. So that will be 11 over 15, which is about 73%. And what does that mean? That means that 73% of the times, or rather, we're not finding 73% of the normal cases. Other way around, we're finding 73% of the normal cases. 27% of the normal cases we don't find. 27% of the normal cases we kind of just predict as something else. We miss them. So an example where precision and recall is really can be important. Let's say that we're predicting something medical, which we're doing right now. And let's look at viral pneumonia. Viral pneumonia has 100% recall. Every time we're predicting viral pneumonia, it is viral pneumonia, or it should be viral pneumonia, right? We never predict viral pneumonia as COVID or as normal. And this can be really important in case viral pneumonia is something you never want to miss. It's fine that if we tell a person they have viral pneumonia, it ends up that they don't have anything, or they have COVID. I don't know if that's true, but let's imagine. But in this case, we don't want anyone to have viral pneumonia, but we don't find it. That's when you want to have really high recall. Precision is when you want to have as few false alarms as possible. In this case, we have a lot of false alarms. When we predict viral pneumonia, we're going to be wrong more than half of the time. However, when we predict COVID, we're certain that they have COVID. We might miss a few COVID cases, but if we predict COVID, they do have COVID. And that creates, so that precision and recall, and they create a bit of a balance between themselves. So the higher precision you have, chances are the lower recall you have. If you make your model more and more precise to exactly predict when they have COVID, they should have COVID, you'll likely start to misclassify a few times. So it actually classifies COVID as normal or viral pneumonia, and the other way around. All right, that was a little bit long-winded, but hopefully that explained how the confusion matrix works and how precision and recall are really important metrics to look at. Now over to the left, we have precision and recall, but we have a average of them. And they end up being the same as the average of a categorical accuracy, which is not very helpful. We're actually going to change this pretty soon. But if we go into the training, we can see precision and recall for each class. And this is where it becomes useful. So here we can see, just like we saw before, the validation pneumonia recall is 1. But the precision for viral pneumonia is horrible, 37%. And this can guide you on what samples you need to train more on, what samples you might need to better classify or create better images for. So even more than accuracy, you want to look at precision and recall when you dig into your metrics or into your model. The final one is the F1 score, or the F score. So what this one tells you is this is a average of precision and recall essentially, but it's not the normal one. It's not even an average. It's a mean. It's a harmonic mean, and it's an alternative to looking at accuracy. What this one tells, real quick, is if it strays towards the lower of the values. So if you have a really good recall but a really bad precision, the F1 score is going to be a bit lower than a normal mean or average. If you have decent recall and precision, it's going to get decent, just like we see the normal here. And if your precision and recall are both good, your F1 score is going to be good for that class as well. So this one is a good way to just get an overview of how your model trained for different classes, how it's a summary of the precision and recall. All right, last thing to go through in the different metrics you can see, and these are just the categorical metrics in PerceptiLabs. You can of course see for segmentation or regression as well if you're training, but classification is a pretty common case, so it's good to cover them. Last one is the top 5 categorical accuracy. Now this one's always going to be 100% unless you have more than 5 classes. This one tells you, so if we look at a prediction of our model, we have a distribution where some classes predicted higher than others. Your model doesn't just return a single class, it returns this distribution. So what the top 5 categorical accuracy, or top K categorical if you want to put in another number here, says is that if it takes all your 5 best predictions, the predictions, the top 5 predictions you're most certain of, which the model is most certain of, it takes those and looks if any of those are correct. Which in this case, we only have 3 predictions, only 3 classes. So one of those 3 are always going to be correct. But if you have 100 classes or 50 classes, it could be interesting to know what your top 5 categorical accuracy is, to know how close to correct you are. Do you have a meh accuracy, but your top 5 is pretty good? That means that it predicts, it's still predicting the class it should be with a decently high certainty. It's just not the highest certainty. So and of course you can also in ranking systems and so on, you can show the top 5 alternatives rather than the top 1, and you can connect those to your distribution. So it's a different way of measuring how well your model performed, with also giving it a little bit of more leeway than just a normal top 1 accuracy. All right, but that is how to use a TensorFlow Hub Model in PerceptiLabs, and a deep dive into the different metrics which PerceptiLabs have, and how to use them. And, well, more than just PerceptiLabs, how to understand and use precision, recall, and confusion matrix, and everything else in general for your deep learning modeling. But thank you very much everyone for watching. I hope you all have a great day, and take care until next time.